P block elements part 2. In the last video we discussed about the physical properties of the P block elements, that is atomic radius and ionization energy. Now we are going to discuss about the oxidation state, metallic property and electronegativity in P block elements. Oxidation state. The oxidation state of various elements are closely connected with the number of valence electrons. In a group, the S block elements show only one stable oxidation state, but in P block elements show more than one stable oxidation state. The maximum oxidation state shown by the P block element is equal to the total number of S and P electrons in the valence shell. One of the important things you should have to study here is inert pair effect. We can discuss this with an example. We can take one of the group from the P block. Here I am taking group 14. We know that in group 14 carbon, silicon, germanium, tin, lead are present. In group 14 elements there exist two oxidation states, +4 and +2. The +4 state is more important in the first two elements, that is carbon and silicon, and the +2 state become more stable as we go down the group. Thus the last two elements, tin and lead, which are more stable in +2 oxidation state than +4 oxidation state. Here we can see that the heavier elements in the group are preferred to show lower oxidation state. We can look the electronic configuration of the group 14. There we can see that Ns2P2 configuration is there. The valence P electrons are lesser probability of being nearer to the nucleus, so that they are easier to be removed or excited to higher orbitals. Because of this, in heavier elements the S electrons are become inert, that is they remain paired and not take part in the bonding, especially in the heavier elements only, and this concept is called inert pair effect. One more time I am repeating. Inert pair effect means the valence P electrons have lesser probability being near to the nucleus, and that's why its electron, the P electrons, are become excited or can be removed, and S electron become inert, and this is called inert pair effect. Now we can move to group 13. In group 13 they have Ns2 and P1 electronic configuration, and they exhibit two oxidation state, +3 and +1 oxidation state. Boron and aluminium show +3 oxidation state, and the remaining elements show +1 and +3 oxidation state. And in down the group, +3 oxidation state decreases and +1 oxidation state increases. This is I already discussed in the inert pair effect. This is due to inert pair effect. An example is here. One of the important example is thallium forms thallium chloride. That is compounds of thallium in which thallium is in univalent are more stable than those of the trivalent. This is due to inert pair effect. Then group 14, here I am already discussed earlier, that is it having Ns2 and P2 configuration, and they exhibit +4 and +2 oxidation state, and the stability of +4 oxidation state decreases down to group, and stability of +2 oxidation state increases down to group. This is due to inert pair effect. One of the example, it is very important in the university examination, that is PbCl2 is more stable than PbCl4. Here lead is in +2 oxidation state, that is which is more stable. Coming to group 15, there we seen that NS2-NP3 configuration, so that they have two choices. There may be 3 electrons can be gained or 3 electrons can be donated. So they have possibility of forming +3 and -3 oxidation state. Because of the small size, nitrogen and phosphorus can more probable to gain 3 electrons to complete their octet, and hence show its oxidation state of -3. That is, nitrogen and phosphorus show oxidations have a chance to form the -3 oxidation state. And also there is 3 half-filled orbitals are present. They also show oxidation state of +3 also. Except nitrogen, other elements show an oxidation state of +5. This is because of the presence of empty d orbital. One of the probable questions from this part is, why nitrogen does not form pentahalide? This is due to absence of vacant d orbital. Now we check the group 16. Here NS2-NP4 configuration. Coming to oxygen first, they have high electronegativity, so that the tendency to gain 2 electrons. That's why oxygen show an oxidation state of -2 only. There is some exception is there. In OF2, we see that fluorine is more electronegative than oxygen, so that oxygen has +2 oxidation state in OF2. And one more exception is there, that is H2O2, where oxygen have -1 oxidation state. This is one of the important probable questions in the entrance examination. Next, all other elements in the 16th group show an oxidation state of +2, +4, +6. This is because of different excitation possible to empty d orbitals. Coming to group 17, there we can see that NS2-NP5 configuration. There need only 1 electron to complete their octet, so that there is more chance to form the -1 oxidation state. In case of fluorine, we know that it is the highest electronegative element, so that we have tendency to gain the electron. So fluorine show an oxidation state of -1 only, and the other elements show an oxidation state of -1, +1, +3, +5 and +7. This is due to different excitation possible to empty d orbitals. Next, we can move to another physical property, that is metallic or electropositive character. Metals have a tendency to lose electron to form positive ions. The tendency of an element to lose electrons is closely connected with the ionization energy of that element. The smaller the ionization energy, the greater will be the tendency to lose electron. That is, greater will be the metallic character. We can simply note that ionization energy is inversely proportional to metallic character. As we know that ionization energy increases in a given period and decreases in a given group, so that metallic character increases as we move down from the group. In group 13, the elements are less metallic as compared to group 1 and 2 elements. This is because of smaller size and higher ionization energy. And in down the group, the metallic or the electropositive character increases from boron to aluminium and then decreases. This is I already discussed. This is because of there is no intervening d orbitals in aluminium, but these are present in the remaining lower elements. Coming to group 14, this is less metallic than group 13 elements as because of higher ionization energy. In this, carbon is non-metal, silicon is semi-metal, germanium is a metalloid, while tin and lead are metals. Now group 15, nitrogen and phosphorus are non-metals, arsenic and antimony are metalloids, while bismuth is a typical metals. In group 16 elements, these have very little metallic character because of high ionization energy. In this, oxygen and sulfur are nonmetals, selenium and tellurium are very little metallic character, while polonium is metallic. In group 17, we know that all the elements have high ionization energy, so that these all elements are non-metals. But some means I didn't show some metallic character, as it can form I plus by loss of electron. Next, we can move to another physical property, electronegativity. As we know that electronegativity is the power of an atom to attract electrons to itself. In a period, electronegativity increases. This is due to smaller size, and in a group, electronegativity decreases due to increase in the size. In the periodic table, the most electronegative element is the fluorine, and the second most electronegative element is oxygen. Here giving the p block elements, here you can easily identify which of them are metals, metalloids and non-metals. This is all about the physical properties of the p block elements. I think all of you understand and you got a well knowledge about the p block elements, its physical properties.